Good morning, everyone. This is the ARMA hydraulic fracturing community Robe Talk series. And it is our great pleasure today. Welcome Professor Anthony Peirce from University of British Columbia. Present the tipping point, how tip asymptotics can enhance hydraulic fracture modeling. Before the talk, I want to thank everyone actually for participating over the past 2 months. Yeah, time really flies when you have fun. We have great speakers, we have great fun. Many of the speakers over the past, all of them actually are inspiring. That's why we have such a large crowd participating today, and the future continues. Beyond this fun, most important things we have done so far is everyone keeps safe and healthy. That's the most important things for all of us to keep in mind. We're still in the woods. We still didn't come out yet. So practicing, like Maurice Dussault, Professor Maurice Dussault mentioned earlier, practicing social distancing, personal hygiene, wear mask. Those are all basics, regardless wherever you are in the world. Besides safety first, and then we have fun, right? Technically, we connected, we entertained, and we stimulated, not only by the speakers, great speakers, but also by participants like yourself. I found the question session actually is become more and more my favorite sessions. It's people asking so many good questions. Today's presentation, for the folks who are not very familiar, I just want to reiterate, pardon me for many times, but those talks are called the robe talks. That means it's carol talks. People might wear their robes. We don't ask any release from presenters, but most presenters have kindly released their presentations through recordings. And we announce those links in the newsletter from the hydraulic fracturing community. If you have not received my newsletter before, you better send me an email. From that point of view, today, Anthony Peirce, Professor Peirce has also kindly offered to release his recording. So you don't need to take up anything from your side, take any actions. But like I said, it's not, we often took it for granted, but really the only reason we have this is to encourage people to communicate and exchange. That's why we don't require people to release anything so that people can open up. Having said that, today, thanks Anthony, not only give us this talk, but also release the recordings afterwards. Many of you know Professor Anthony Peirce probably more than I do. He is a professor, well-known professor, as a matter of fact, in the Department of Mathematics at University of British Columbia. Many of our students, his students become, including Andy Barnger and the folks on his list, on his president list, become active stars in this field. Professor Peirce got his PhD in Princeton University as a Fulbright scholar. Prior to his PhD, he worked actually as applied mathematician at the Chamber of Mines Research Laboratory in South Africa. And then he has been leading this research group in hydraulic fracture, in fracture mechanics, especially the instability in elastoplastic materials, development of specialized numerical algorithm for model large-scale rock fracture process, and many other aspects. So with that, I leave the floor to Anthony. And one last thing, if you have any questions, feel free to type into your chat window. We have 45 minutes, or maybe extend a little bit more. But after the presentation, Anthony will answer those questions from the chat windows. If the time is running out, he also has offered to answer the remaining questions through the emails, which I will release, copy his email if you not already have. Anthony, feel free to take over. Thanks.
Thank you, Gang. Much as I'd like to have had Andy as a student, he wasn't a student, he was actually a student of Emmanuel's, but Andy's a valued collaborator. Anyway, thank you, Gang and Andy, for organizing this series so professionally and giving me the opportunity to share some of my ideas with you. I'm going to be focusing on the tip and how it affects hydraulic fracture modeling. Hopefully I'll be able to convince you after this talk that you shouldn't ignore it. It's actually not something that we should run away from, but something that we should embrace and utilize, because it actually has a lot to teach us and a lot that we can use. First of all, a lot of the material that I'm going to be talking about is available on my website. And I'd like to acknowledge collaborators, Andy Bunga. He's provided amazing experiments, as you all know, and also challenged us in our modeling efforts. And Emmanuel de Tournay, sort of the master of asymptotics in hydraulic fracture modeling, and Yegor Dontsov and Lisa Gordelli, they were both postdocs with me. You know, you heard from Yegor last week. You can see what a talent he is, and Lisa worked on developing asymptotic methods for the extended finite element method, among other things. I've also included Eddie Siebritz in this because he was responsible for getting me involved in this whole enterprise in the first place. So he deserves a mention, or the blame, I don't know which you want to call it. Anyway, I just wanted to, I'm not going to give you a detailed outline. I just want to put some ideas out there. And I think many of you possibly haven't heard of the word asymptotology. And it was introduced by a famous applied mathematician, Martin Kruskal, who actually also coined the word soliton. And he described asymptotology as the art of dealing with an applied mathematical systems in limiting cases. And often these limiting cases lead to challenging numerics, long time behavior near singular points, etc. And typically asymptotics or asymptotic analysis leads to a simplified system or simplified systems. And we're going to see this in the context of hydraulic fractures. In fact, the system of equations for hydraulic fractures is no exception. It also succumbs to asymptotic analysis, and in fact, I go so far as to say, for the hydraulic fractures, the tip is the tail that wags the dog. It's actually crucial to understand what's going on in the tip, and rather than running away from it, which one's inclined to do if you just want to throw mesh points at things, you know, it's actually a nasty place for a numerical analyst. But if you embrace the tip asymptotics, it can actually be very useful. So those are the take-home messages. Right, so I'm going to be talking about continuum numerical models. This is in this, you know, we've We heard from Branko about discrete models, you know, the distinct element modeling. This is continuum models, and they fall into essentially two classes: boundary integral formulations, where basically if this is a 2D material here, and your fracture can be isolated to a curve in 2D. And the beauty of this is that you only discretize the boundary, but the problem is that you limit it to linear elasticity. So that the pluses and minuses in any sort of modeling enterprise. And if we had a 3D fracture, a planar fracture, for example, in a 3D material, then we'd only have to discretize this fracture plane. So that's a big advantage because it substantially reduces the number of unknowns that we need to track. The finite element method is always sort of the go-to analysis method for engineers. They're fantastic at modeling nonlinear materials, plasticity, for example. But you know, you can see it near a crack, you constantly require remeshing, which is a problem. So the extended finite element method was introduced by Belichko and co-workers. It can model nonlinear materials, and it avoids remeshing, basically recognizing that there's some singular behavior at the tip. You can enhance the basis functions here to capture that behavior and then incorporate it and get the sort of convergence that you would expect. So you don't have to do remeshing. You can sort of pass through a mesh like this. All right, so given that, I'm going to just jump straight into the KGD model. I mean, many of you are possibly familiar with this. I don't know, to talk about asymptotics, unfortunately, the devil is in the details. So I'm gonna have to put down some equations. So for those of you for whom this is not your taste, then I apologize. But so this is basically an expression of conservation of fluid, essentially, or keeps track of the fluid. There could be fluid losses. This is the Carter-Leakoff. We're assuming a Newtonian fluid here. And this is a zero flux boundary condition, so we're assuming fluid isn't moving out of the tips. F is the fluid pressure, and W is the fracture opening. There's fluid being pumped into the crack. There's confinement. There are viscous energy losses. To open the fracture, to break rock, you have to release energy, and that's related to this asymptotic behavior, which is related to the fracture toughness and the stress intensity factor being equal to the fracture toughness as the fracture propagates. So, and then there's this is the balance of forces, essentially that everything's in quasi-equilibrium. So this is the pressure that's exerted on the fracture surfaces minus the confining stress, and this is related to the fracture opening. And this is a singular integral equation, which is nasty. And there's another nasty thing that happens here. We basically, close to the tip, and this is really the source of all problems. I mean, or one of this, well, this exotic behavior, put it that way. Close to the tip, W goes to 0. So as W goes to 0, the pressure gradient is free to go to infinity, and the product can be finite. Okay, so this is what in mathematics we call the distinguished limit. So you can get something that's finite and will balance with these terms, but the quantities are either going to 0 and infinity. So this makes it particularly challenging to capture numerically. Yeah, and this is, for a mathematician, this is known as a degenerate partial differential equation. Okay, so enough of that. One of the other things I just wanted to mention, and this is quite crucial, is the fracture length is not known a priori. So that's actually the million-dollar question: where's the fracture going? And these two equations, if you knew the fracture length, these two equations can be solved relatively simply as a coupled system. But in fact, if we don't know where what the fracture length is, there's an uncountable infinity of solutions. Because this is a nonlinear system, we can have an infinite number of solutions to the problem. So, and in the region, if we specify a slightly different width, we'll get a different pressure, and slightly different fracture length, we'll get a different pressure and width. And they'll all equilibrate and match volume balance. So that's one of the challenges, is to catch this free boundary. Okay, one of the things, if you discretize it, I'm going to represent it as this operator equation for the fluid flow and the elasticity. So that's just sort of introducing some notation going forward. Right, so let's just jump straight into it. So think of ourselves as a surfer on the tip of the crack, and we're looking backwards, and we introduce a coordinate system going backwards. Okay, this is the length of the crack. And we introduce a variable. If W is the fracture opening, W hat would be the width expressed in this new variable, and plugging in, and we can use the chain rule, we end up, this time derivative ends up giving you a time derivative, just applying the chain rule, differentiating with respect to x bar or x hat, and then this with respect to time, we get this derivative, this convective term. And the spatial derivative stays the same. Okay, so with respect to x, it's just the negative. Okay, so that's essentially just the chain rule, and the differential equation boils down to this. You get this convective term, and this is the lubrication term, and the amount of fluid you're pushing into the fracture. And transforming coordinates, this is the tip now, and that's the other tip, if you like. So everything's sort of basically the same, but just shifted, and the variables have been renamed. Okay, so nothing really has happened. I've just moved myself to the tip of the fracture. Okay, so now this is what an applied mathematician typically does. You zoom into the tip and see what behavior happens, right? So this is a device where we basically thinking of delta as being a small parameter and epsilon as being another small parameter. Okay, and you plug this in, and it's again just the chain rule. And these things just boil down, these things, these epsilons and deltas come out here. So now what we can do is we can balance certain terms. If we balance this one with this one, we get epsilon is delta to the 2/3, and that's actually just essentially identified what we call the viscous asymptote. Okay, if we match this term with that term, then we end up with what's called the Leakoff asymptote. Notice in the viscous asymptote, if epsilon is delta to the 2/3, then epsilon over delta is going to give you delta to the -1/3, and that's certainly going to be bigger than delta to the 2/3. So basically, this term becomes irrelevant in this asymptotic limit as we move to the tip. So this essentially makes these equations time independent and what we call autonomous. Right? So sort of zooming into these equations, another look at this is what happens if we looked at the equations if we assumed that W had a power law. Okay, so plugging this into the governing equations, it just turns out, okay, just taking the derivative, you get s to the alpha, if you like, and or s to the alpha -1, and it just turns out a simple calculation with complex analysis will give you this relationship. Okay, so this is just some, you can look this up in a table of integrals if you like, but it's quite profound. But because it's actually telling you that this function here is an eigenfunction for this integral operator, because basically it reproduces itself, and this is the eigenvalue. Okay, so let's look at the lubrication equation, and basically, if we close to the tip, we can rewrite the distance in t minus t naught in the Carter-Leacoff as the distance over to the of the tip divided by the velocity, and the equation reduces to this, and we can integrate, and we end up with this reduced equation. So there's the reduction that you get that we were talking about in terms of asymptotics. So for the K vertex, so this would be if it's in the toughness mode of propagation, so W is x to the half. So we can cancel a W here and a W there. So we get W squared. So x to the half squared just gives you x. So dp dx tells you that, I mean, x times dp dx is equal to a constant. So dp dx is v over x, essentially, which tells you that integrating it's a logarithm. Notice that for alpha equals a half, you don't get, it doesn't generate any stress, any pressure. Okay, so that's what sort of degenerate eigenfunction. So you have to go to the lubrication equation to actually find what the pressure is. Okay, notice that the pressure in this special case is singular, right, as well. Okay, so now if we assume alpha is not equal to a half, plugging in, these power laws look like this, each of these terms. And if we match this term to this term, for alpha minus 2 equals alpha, we get a 2/3 power. And that's the viscous asymptote. Similarly, if we match this term to this term, for alpha minus 2 equals a half, we get this 5/8. Okay, so there we go. So those are the three asymptotes. All of them cause singular behavior. Now, what about the asymptotes and multiscale behavior? So I just thought, well, it might be instructive. We all know that if x is less than a half, the smallest power is the largest function. Okay, so half. So this is the sort of ranking for x to the alpha. Okay, so you think, well, the toughness always dominates. However, if we look at the asymptotes, that's true. However, these have the velocity in them. Okay, so the coefficient can cause either of these two asymptotes to actually be bigger than the toughness asymptote. This one is constant. However, so depending on the velocity, the situation can arise where either of these or both of them can be bigger than the toughness. But ultimately, as you go to the tip, the toughness is always king, right? So it's sort of speaking to, on multiple time scales, multiscale behavior. Okay, that can happen, and we're going to see that. Okay, so again, the pressures are all singular, which is bad news for a numerical person. Okay, so a big development was by Dimitri Garagash, Emmanuel, and Jose Adachi in 2011, where they were looking at basically trying to come up with a universal asymptote. And basically, we've identified these vertices, but what happens in between? Okay, so here's that reduced system that we've been talking about. And basically, they analyzed the transition from the K vertex to the M vertex, for example, or the K to the M tilde, which is the C. I use M tilde and C sort of interchangeably, by the way. C being for Carter-Leacoff. So this is viscous, this is viscous, toughness, and Leacoff vertices. And what happens in between? Okay, so you want to join each of these. So we know that close to the tip, the fracture is going to be behaving in a toughness mode. But where does it go there? I mean, as you move away from the tip. And sometimes, if there's no Leacoff, this is known as the MK edge, it'll move out to a viscous regime. And there's something in between. Or if there's sufficient leak off, you'll go close to the leak off regime and then back to the viscous regime. So this is a sort of plot that Diego Donsoff has sort of popularized in phase space, basically. If you're moving back out from the tip, this is distance from the tip. Here, this cross section shows that essentially you're going on one of these trajectories. You don't encounter, there is some leak off in each one of these, but not enough to actually get to the leak off regime. However, at some stage, I mean, if the velocities are right and the leak off is correct, and it's all determined by this parameter chi, which I haven't mentioned, it's really it's essentially related to the amount of leak off. Basically, you can go from toughness to leak off dominated to viscous. So if you look here, this is that little piece of this fracture, and then if you zoom out, it's all leak off on this scale, and if you zoom out, then basically that's where the leak off is according to the viscosity. So this happens on many decades of a huge time length scale. So how on earth can you capture all this behavior numerically? Okay, so I'm just sort of going to this slide where there's sort of challenges with numerical modeling. Basically, you've got the lubrication equation. If you put these together, it gives you a stiff system. So that's hard to time step. You've got to use implicit time stepping typically. You've got a singular pressure field. At the tip, the pressure goes to infinity. And you've got multiscale tip asymptotics going down several decades. So I mean, to model that on a field scale is almost hopeless if you're going to try and, I mean, onto the computers we have today, even though we've got lots of memory. And it's got this, what I call a singular free boundary problem, because basically you can't just use the fluid velocity to determine where the tip is, because W is going to 0 and this thing is going to infinity. And how do you do that numerically? I mean, most numerical methods are assuming Taylor's series. So it's hopeless near a singularity. Right? So that's the problem. So Emmanuel and I came up with this implicit level set algorithm, which uses the the sort of epiphany was that rather than running away from the asymptote, use it to find where the tip is. So just think of yourself in a typical time step, and you've got an estimate. You assume the fracture is there. You've got an estimate of the fracture opening from the equilibrium equation, the fluid volume balance and force equilibrium equation. And then what you can do, I mean, I'm just illustrating here. W is K prime E prime S to the half. That's the toughness asymptote. You can invert this relation, and knowing W, you can find what S is. So we can find out where the free boundary should be. So just use the asymptote to get the free boundary. And then you think, oh, but hang on, I'm chasing my tail here. Because W, I mean, this asymptote has the velocity in it, right? So if we try to invert, we've got the velocity, which is an unknown. Okay, that's the thing we're trying to find. However, we can replace that with a difference. And now we get a little cubic. So here we can solve explicitly. Here we've got a cubic equation in S to determine where the free boundary is. Okay, so given that we've got the fracture width, we can determine what the tip width is by actually averaging the asymptote in the tip. And notice this fracture, this element is partially filled. So it doesn't matter, as long as we calculate the average asymptote in the tip, it gives us an excellent solution. And basically we match the volume, the amount of tip that was in the fluid plus the amount of fluid that flowed in the time, and that's given by this pressure gradient relation. And the tip width is known, so we need a variable in the tip to be solved for, and this pressure in the tip is unknown. So that pressure in the tip is specifically determined so that the flux across the boundary is matched. to the amount of volume in the tip. So that's it. So now, how do you use this in a multi-scale behavior? Now, I've just turned the tip around just to sort of fit in with Jaegel's diagram. So there's the tip width. And basically, what we do is we map this onto, we map this tip width onto this asymptote. And basically, we integrate the tip asymptote from 0 to L, and we've captured all this sorry, I've got a finger trouble here. We're capturing all this multi-scale behavior, but what I call in a weak sense, because it's actually just the integral over that behavior. In all of this, the tip velocity is like a parameter, which we solve for all the time. Okay, so I mean, basically, we sweeping under the rug all of this multi-scale behavior. By the way, this is not unprecedented in modeling. For example, when we use a linear elastic fracture mechanics, we're sweeping under the rug a whole lot of stuff that's going on in the process zone. Okay, so I mean, this is not unprecedented. But what we are able to do is to represent and capture a lot of multi-scale behavior on a coarse mesh. So here's just a bit of an animation of how it goes. Basically, there you got the estimate of the width. Here you get a new estimate of the width. Find where the asymptote is. Set the tip tip width, and then you solve for the pressures and widths. Get new estimate until the whole process settles down. And you can see, even though we're using piecewise constant elements, we're getting a pretty accurate representation of the solution. I'll just let it go one more step just to see how. So you pump in a bit more fluid, you get the first estimate of the fracture opening, find out where the fracture boundary is, put in the tip, let it update, capture the width, and now look at the fracture. I mean the solution. It's almost right on, and we've only got like 5 elements. So it's able to capture the tip asymptote really accurately and represent all that fine scale behavior. Okay, so with Lisa Godelli, we took this into the XFEM world. Basically, XFEM, as I said, basically you enhance the normal basis functions for finite elements with step basis functions to represent a crack. So here's a cracked element. So there's the step. And close to the tip, you enhance the basis functions here with a tip basis function, which by looking at the elastic solution for an arbitrary lambda, you can come out with this fundamental set of basis functions. And that enables you to set the widths in the tip and solve for pressures backwards, and then come up with what we call an implicit level set scheme, similar to what Emmanuel and I were talking about. So there are a number of papers on that. So here's an example where we were able to sort of look at a curved crack, and this is a comparison with other, this is a boundary integral code that Lisa and Emmanuel developed, and it matches pretty well. And here's even a little animation of the crack path. Right, so now onto the planar HF equations. It's pretty similar. We've got an elasticity integral equation, a lubrication equation, and boundary conditions, propagation conditions, zero flux. And we're still stuck with this width in the tip. The width goes to 0 and the pressure gradient goes to infinity. So we discretize this. Same old problem. We've got this evolution equation that's stiff, and we've got this singular free boundary problem. So here, I just want to do a little thought experiment with you. I mean, think of yourself, if we think of ourselves as ants, and we're walking close to the tip. As we get closer to the tip, the tip starts to look like a flat object. And we experience this every day. We live on a curved surface, yet the world looks flat. I mean, many people still believe that it's flat. But so as you get closer and closer to the boundary of the crack, it looks like it's flat. So, and it looks like it's going off to infinity. So that puts you in a state of plane strain. So here's a sort of limiting process. This is something that only should be done between consenting adults. But the take-home message is we can take that 2D integral equation, integrate it over this region, and reduce it to the plain old KGD plane strain kernel. I mean, that's the take-home message. And the same happens for the lubrication equation. I mean, that's a little bit less complicated. So locating the free boundary now in 3D, or for a planar fracture, we have what we call survey points, where we get the asymptote, we look to the distance to the free boundary, and then essentially what we do is we solve this so-called iconal equation. So here, from the survey points, we find the distance to the free boundary, and we evolve this thing forward in time, and lo and behold, by solving this PDE, we can actually end up determining where the free boundary is. So this is a sort of a very robust way to determine where the free boundary is. I mean, this comes from fluid mechanics and conservation laws. So this is a standard way to solve free boundary problems, and it's called a level set method, if you like. So that's why we've called it the implicit level set method. So just to give you an idea, here was the distance to the free boundary at the survey points, and these are all the distances to the tip, and you get this level set surface. I mean, or the sign distance function, and the level set is this intersection with the with zero. So you can actually locate the free boundary pretty accurately and simply with this method. So multiscale ILSA, same idea. Basically, if you move close to the tip, everything becomes plane strain. You've got the same multiscale behavior. I mean, this was something, a really neat reduction that Jaeger introduced. Essentially, those governing equations can be manipulated so that this looks like a delta function. So approximately, this looks like a differential equation, an autonomous differential equation. And you can solve that approximately and come up with a sort of implicit version of the complete generalized multiscale asymptote. So basically, we plug in the widths, and we use Newton's method to find out what S is, and that tells us where the free boundary is, and that's it. Okay, so just some simulations. Yeah, this is a comparison between the level set method, which is in black, and the gray lines. This is a beautiful experiment by Andy Bunger of a P3D kind of geometry, a fracture going through stress barriers, and the ILSA scheme matches the experiment pretty well. Now, if you want to put multiscale behavior, put toughness in, basically, I got the color scheme mixed up when I did this. The red line is the viscous asymptote, and this coloring is basically telling you where on the asymptotes you are. So here it's very tough, and there it's viscous, which is what we know, and a slightly higher toughness. I mean, this is a dimensionless toughness here, and you can see how the free boundary changes. This is actually something that is quite amazing. We've used, now you can, just an illustration of how you can use a complicated model, a complex model, to calibrate and come up with reduced models. So one of the things when I was looking at P3D kind of geometries, I was looking at how does it actually compare with the classic P3D model. So when there's viscosity, I mean, when you're in the viscous mode, this is Andy's experiment, and this is the solid line is the ILSA solution. And P3D, the classic P3D gives you this answer, which is not too bad. I mean, the fracture length is okay, and the width is not too bad. However, when the solution is tough, when there is toughness, P3D gives you this as the solution, hopeless, and ILSA gives you this. So this inspired Jaeger to go and do some of his reduced model magic, and he managed to match the P3D, adapt P3D, which is EP3D, the extended P3D model, and now it matches ILSA within a few percent. So there's an example of how you can use these more complicated models to calibrate simple models. By the way, ILSA's, Jaeger's reduced model computes in seconds, whereas ILSA would take a few hours to do that, or if not a day. So you can also do MKC, you know, the multiscale asymptote, and here you can see the coloring is basically all those elements along the boundary. These are the survey elements. So each of these elements, each of the fronts are moving at a different point in this multi-scale space, but it captures all of that behavior. And here's with large leak-off, you can see it's accessing the large leak-off, and the coloring tells you which mode each of the fractures are propagating in at that very time. And here's a stress drop with a medium leak-off. Okay, so I think you've got, and now we've done it with multiple planes. You can see some stress shadowing going on. We also extended it to capture, to look at turbulent flow. I'm not going to dwell on this, but basically you can come up with a correction to the viscosity that will determine the effect of turbulence. And fortunately, close to the tip, it's laminar, and it's basically determined by the Reynolds number and this roughness parameter. So you can see here's the viscous solution, and here's the, laminar solution, and this is the turbulent solution. And this is because the pressure is more pronounced. You can see these lines are where the turbulence is active. Okay, and lastly, I've also extended this to the ILSA scheme to be able to work on an unstructured triangular mesh. So we're not restricted in our geometries either. This is sort of looking towards doing planar, non-planar fractures. And now I'm going to go back to the take-home message. So asymptotology. So I think the tip is the tail that wags the dog in hydraulic fracturing. And don't be scared of the tip. Embrace it. It can be very useful. And that's all I have to say. Thank you.
Thanks, Anthony. My brain is spinning actually. It's very insightful actually. Reminds me a lot of things. Especially, honestly speaking, we in the industry we've been dealing with so-called legal phenomena, and who is driving the hydraulic fracture, whether tip, as some people mentioned, the rock strength is nothing compared to, especially when the fracture become long enough, and the viscosity of the fluid itself. So these three components that you explained very well. It's actually, I try to connect what you said with what my experience is. It's actually make a lot of things. Thanks. This is fantastic. For the folks, feel free to type your question. I see some of the question type in the chat window.
Okay.
Anthony, feel free to answer those questions.
From SAS, I'm seeing no fluid lag here. What's the chance for a model code that has no that does not account for fluid lag to reproduce the major features of HF crack propagation? Okay, so I think Dimitri, Garagash, and Emmanuel showed that in high confinement environments, basically the fluid lag vanishes exponentially fast. So we are assuming that basically, I forgot to mention that, and thank you for asking that question. We're assuming that there's a coalescence of the fluid front and the fracture front. And I mean, this is what's causing this devil's mix. Okay, so in fact, modeling with a fluid lag is quite a bit simpler. We are looking at the difficult case where you don't have a fluid lag, which often occurs when you've got deep reservoirs. Okay, so I think does not account for fluid lag to review. So I think, I mean, it all depends. If you're very close to the free surface, obviously the fluid lag is going to be important. And I mean, essentially, then it's just going to be a dry crack. What we call it, it's going to be fracture toughness is dominating the movement of the crack boundary. In particular, under what conditions where the fluid fraction is not expected to be about 1. The fluid fraction. I'm not sure exactly what that means. By the fluid fraction. Anyway, I'll move on. I mean, maybe you can type some more. I probably missed it, but the leak off is ignored. Is the viscous asymptote exponent still? Yeah, I mean, if there's no leak off, if it's in impermeable medium, then the viscous asymptote is 2/3. The thing is that if there is, sorry, let me just, oh Lord, I've lost the chat. I just wanted to get out of this thing. Sorry, that's what I wanted to do. So let me just go back to this picture here, or here. If you have a look here, I mean, basically, you can get to a situation over here where there's no, there is leak off, but you don't access the leak off asymptote. Here, you'll see the leak off asymptote come in. So it depends on the amount of leak off. You still ultimately will get you always ultimately get the 2/3 asymptote, but it happens further away from the tip. And these are in scale coordinates. So this could be on the scale of 1 element, right? Okay, so I hope that, Varun, I hope that answers your question. Peirce, the effect of fluid lag has been introduced. Oh, Peirce answered my question. Okay, thanks, Peirce. Yeah, okay. I'm sorry about that. I should, regarding fluid lag to everyone, model is not accounting for it. So I don't know if I need to say any more about Peirce. Thanks, Peirce. Okay. Will volume balance function be checked during the fracture front iteration process? Yeah, volume is always basically, because we do a pressure width solve, we're constantly adjusting the volume balance. So volume is balanced to however accurately you solve your system of equations. Varun, for the stress-based fracture propagation criterion in toughness dominated problems, the ERR condition can be converted to a stress-based by using asymptote half. Can we I guess, I mean, if it's viscosity dominated, I think you can probably get away with using, if you use the wrong asymptote. We've done experiments like this. If you use a toughness asymptote but with low toughness, I mean small toughness, it will kind of match the viscous solution, but it's not very efficient. So it's a matter of you're going to spend more, you're going to have to use more mesh points to capture the solution properly. So it's a matter of I mean, if you actually use the right asymptote, you can get away with the biggest murder you can. I mean, you can get away with murder basically. Otherwise, you're going to pay. To get an accurate solution if you use the toughness asymptote. How much can the tip asymptotes affect the inlet pressure? Well, that's all sort of transmitted back when you do your pressure width solve. Olga, Olga Chris, hi Anthony, the presented asymptotes are for Newtonian fluids. Did you implement asymptotics for? Yeah, I have, but that project isn't finished yet. I seem to be a little bit like Emmanuel. I have projects that go on for decades. Yes. Okay, Alexei. There have been some publications of reformula in terms of fluid velocity, which is a smooth function. What are the pros and cons of using this approach? I think when you're dealing with leak off in a 2D, like for a planar fracture, it's not so easy. In answer to, I mean, it does make sense because the fluid velocity is a beautiful quantity. It is the distinguished limit, and if you can formulate the equation so that you get that as a primary variable, yes, it's natural. But then I think when there's significant leak off, I think it's difficult. And in 2D. Any more questions?
Yeah, while people might have more questions, just one thing, reminder the folks. So just the forecast for next week, actually, we all have